So we have just graded your homeworks. I just wanted to take a look at them. So I'm holding them in my office. I guess you can pick them up from your TA anytime starting tomorrow, right? Midterm exam, you mean? Right, so can we have it next week actually? Maybe we'll have enough material. Huh? Sometime on Thursday, maybe. What is the usual time allocated for exams here? So you can ask questions accordingly. Do you have an exam for 50 minutes or for 2 classes, for 2 lectures?
2 hours.
2 hours?
Yeah.
Okay, so it's gonna be like, okay. Okay, then we can reserve the last 2 hours on Thursday for the exam. Huh? Huh? Is it okay with everyone? Okay, then what is the date gonna be then? So today is 7th, 14th, 16th, and 16th, right? It should be 16th. 16th. So the midterm is then gonna be on 15th. So today is the 7th. Isn't it 7th? 7, 7 plus 7, 14, 15, huh? 16. I guess it is the 16th. So 16th July, right? So this is supposed to be Thursday, the midterm exam. And the times are going to be then, we can start at 2:40, and I can let you stay here till 4:30, huh? Okay. All right, so you will be responsible anything up to and including Markov chains, huh? It's also fair, right? And then let us finish Markov chains today. We better finish it today so that you have enough time to think about these topics. Okay, last time we started discussing the long run, right, behavior of Markov chains. Right, so as before, I'll just denote by X. So this is the sequence of random variables. The Markov chain, okay, on some state space, which I will specify for the next couple of classes as the finite set consisting of state 0, 1, and n, right? And we will also denote by P the one-step transition matrix for this chain, right? With one-step transition probability matrix P, and we will call P in Markov chain itself X, right? Regular, right? If for some integer k, right? For some integer k, if for some integer k, all of the entries of the kth power of one-step transition matrix P are all positives, okay? Are all strictly positive. Well, I used all anyway. Okay, strictly positive. Okay, and we'll just state, but we are not going to prove this. We will use this result. So every regular Markov chain, right, is so-called limiting probability distribution. which we will denote by pi. In this case, well, we have n minus 1 states over there. Okay, so this is a probability distribution on the same set, on the same state space. Right? So every regular Markov chain, right, has limiting probability distribution pi. What do you mean? What do we mean by this? Well, all of them are, of course, numbers between 0 and 1 for every state in the state space, for every state I in the state space. And when you sum them up, right, you get 1. And finally, so then the name limiting probability distribution comes from this last statement, which basically says that pi j is the limit as n goes to infinity, the probability that at time n the chain is in state j, starting initially from any arbitrary state I. So this is true for every I and j. Right? Okay. So you can interpret this last line as, in the long run, okay, in the long run, the probability that, right, the chain is going to be in state J, right, this one, starting, well, so that actually needs a clarification later. Okay, going to be in state J equals approximately, right, to pi j irrespective of the initial state. Initial state I. Okay. Right, so you look at this statement, right, no matter where you start, right, as n goes to infinity, so for large n, that's what we mean by long run, the probability that we will find the chain in state j is going to be given by this number pi j, right? So if the probability, once the transition probability matrix is regular in this particular sense, we know that that chain is going to have a probability limiting probability distribution of this sense, right? And we will see in a moment that this is also related with so-called stationary probability distribution, which is going to be very useful in quantifying a lot of interesting measures related with the Markov chain itself. But first, maybe we should also comment on how we can further identify or check whether a Markov chain is regular or not. The definition is already something that you can always use to check. If for some k, you can identify a number, an integer k, for which the k power of one-step transition matrix, which is the same as what? The k-step transition probability matrix, right? We showed that earlier. And what this basically says, you can always, if you know that this matrix, all of the entries of this matrix are positive, then between any two states, right, in the state space E, between any two states, I and J, you can find a path of positive probability that goes from I to J. And that says, actually, I can be reached from state I with positive probability, right? And this is true for any choice of I and J pairs, right? So you can go from I to J, you can come back from J to I, And one of the conclusions is that this chain, Markov chain, is irreducible. That's the name. For that between any two states you can always find a path, or with positive probability you can actually reach any state from any other state. Right? And the other thing that we will notice in a moment is actually okay, actually we need more than this. So maybe this is more than just what it is. So this piece of information is easier to use to identify or to check whether Markov chain is regular or not. Right? So every finite state, this is important actually, every finite state Markov chain, right, satisfying the following two conditions is regular. The first one says, that's connected with what I said about the irreducibility. Okay, I stated it anyway. So the Markov chain is irreducible. Okay, now I'll explain it. Namely, you can always find a path between two states, and that also has a name actually. You may come across these words actually, some of the textbooks. Every state, okay, Markov chain is reducible, namely every state is reachable from every other state, right? And more precisely, right, you can always find, okay, for every ij in the state space, so maybe I can just write like this. For every ij in the state space, there are states like I1, I2, and let's say IR, such that probability of going from this state, initial state, right, or the first state that I picked up earlier, probability of going in one step from I to I1 times the probability of going from I1 to I2 in one step, and so on and so forth, and probability of going from IR minus 1 to IR, and finally going from state IR to J. When you multiply all of them, you get a positive number. In other words, all of them are positive. But we know that this product on the left-hand side is what the probability of going from state I to J through the states I1, I2, and IR. Right? So we derived actually such things at the beginning of our discussion of Markov chains when we introduced the Markov property. Right? So this is one of the conditions. If you know that any two states are reachable from every other state, and if you also know that the chain is aperiodic, okay? For example, if for some of the states, probability of just going back to the same state in one step is positive, that is enough to make sure that the chain is aperiodic, right? Then we know that the chain is regular, this Markov chain is regular, right? And therefore, right, so this conclusion follows, namely, that particular chain will have actually a limiting probability distribution in this particular sense. Okay? And we not only know that Markov chain has limiting distribution, some distribution over the state space which satisfy basically this relation, but also that this thing is unique solution of a collection of a system of linear equations. Right? Moreover, right? Okay. Maybe I should just write it as a theorem. Let me also state it just the way your textbook also does. Okay. We will refer to this result later as we solve examples. Okay. If you are given a one-step transition probability matrix P which is regular, okay, then we already know that the corresponding chain has a limiting probability distribution, but we also now know that the limiting probability distribution pi, okay, defined on this state space E, which consists of n plus 1 states, right, for this particular, for our particular system, is the unique non-negative solution of the following system of linear equations. So we will use actually this system of linear equations in order to find this limiting distribution of the regular Markov chain whenever we need to use this distribution. Okay? And this, there will be one equation for each state which basically says that pi j equals pi I times the one-step transition probability going from I to j, and here I is dummy, and you are summing over all states in your state space. Okay. In this case, we know actually what the state space contains. Perhaps I can just write this as the sum from 0 to n, right? State 0, state 1, state 2, and so on until state n. And we will have one equation for each state. 0, 1 through n. Okay. And then, of course, we also have to make sure that this is a probability distribution on the state space E. We already required this, we are only interested in the solution of the system which are non-negative. We also have to, we also here make sure that the sum equals 1, right? So this is also the requirement for something, a sequence, to be a probability distribution. Okay? All right. Okay, now what did we learn by now? Now, if you come across a Markov chain which has finite number of states, right? And if it is regular, in this sense, right, namely for some k, all of the entries of the k step transition probabilities are all strictly positive, right? Or let us say these two conditions are satisfied, right? Both of them are actually sufficient conditions for what we call, what we say that the x is irreducible and positive recurrent and aperiodic. If we have time, I'll just revisit all these things. Okay, they are properties actually shared by the states of a Markov chain as long as they actually communicate with each other. And that theory mostly important in order to search for the sufficient and necessary conditions for a limiting probability distribution to exist. But I would like to first make sure that we know what it is a limiting distribution and what it is useful for. So we will use them to answer important applied problems, and then perhaps we can come back and study further when exactly this regularity is being satisfied by a given Markov chain. Even if it doesn't have, even if it has countable in the states, under certain circumstances, a Markov chain will still have actually is going to be regular in this particular sense, and then you can still talk about its limiting probability distribution, and all the theory can be actually generalized for that case. But for the timing, so if you have a finite state Markov chain, right, with these two properties, then it is regular. Then we know that it has limiting probability distribution pi, which can be found as by solving these equations, because it is going to be the only solution of this system of equations, right? So we have that, and these equations, right, actually define in general what we call a stationary probability distribution. So in general, any solution of the system of equations, in general, any solution, any non-negative, right? So non-negativity is not over there, right? Any non-negative solution of the equations in star is called, there are several names which are all used actually interchangeably, but they actually emphasize a different property of this distribution. So, for example, it is called the equilibrium distribution, or stationary distribution, or steady state distribution of the Markov chain, right? And what this theorem basically tells us, if X, right, Markov chain, is regular, then it has unique. Okay, let me just pick this one. Your textbook uses word stationary to refer to this one. I'll also explain why also it makes sense to use the other two. It has unique stationary distribution. Okay, which coincides with the limiting probability distribution of the same Markov chain, right? How did I arrive to that conclusion? Well, if the chain is regular, right, we know, according by this theorem, that this system of equations, right, has exactly one solution, right? And therefore, well, since we already agreed to call any solution of this system of equations a stationary distribution, now by theorem we know that there is exactly one solution, and therefore there will be exactly one stationary distribution for this, for the corresponding Markov chain. And we further know that actually that stationary distribution is nothing but the so-called limiting probability distribution. Namely, the stationary distribution of this Markov chain, right, by definition solves this equation, but also has this property. And the stationary distribution coincides with the limit of these conditional probabilities as n goes to infinity, right? No matter what the initial state is. Okay? So we have all these things. You may ask, actually, in general, can you come up with an example where any one of these, let's say, uniqueness may break down, or perhaps X is perhaps stationary distribution does not exist at all, or you may have the stationary distribution but the limiting distribution doesn't exist. Right? Such cases can happen, right? And for that reason this result is non-trivial. Right? You can say, for example, okay, maybe we should actually comment on these things so that you this remark may help you appreciate actually the result itself. So a stationary distribution in general may not exist at all. It is enough to give an example just to convince you. Right? That there is this so-called right shift Markov chain, a very trivial chain. Let's say on the non-negative integers, if you are in state 0 with probability 1, you go to state 1. If you are in state 1, in the next step with probability 1 you go to state 2. It goes like this. Okay? This is the so-called right shift. At every step you basically shift to the right. Right shift Markov chain. Okay? And when you, for this one, so what is this? This is state transition diagram for the chain, and there are always one arc going out of each node to the next with probability 1, right? You are moving to the right. And for this one, for example, you can try to write down this equation, the first one. So pi j, right, in this case. So if j is here, right, and what does this, the right hand side equals to, the right hand side equals, for every I, right, from which in one step you can enter into state I, you multiply pi I with the corresponding one-step transition probability. So now if you are looking at state j, in one step you can enter to state j only from j plus j minus 1 according to this specification. So on the right hand side you will only have what? Pi j minus 1 times p, right, one step transition probability from state j minus 1 to j, which we know equals 1. So this is not this equation, that equation for this model is going to give you what? Simply pi j minus 1. Right? And then this is true for any j starting from 1 going up, right? So you have then pi 1 equals pi 2, which equals pi 3, and so on and so forth. And in fact, it is also true for pi 0, right? Starting with 0. Okay? And that's a trivial, but it looks like, well, actually, you can see that this cannot be really a probability. You cannot get a probability distribution out of this because there are countably many of them. If they are all positive, right, when you sum them all up, then you will get an infinity. So there is no way to really find a pi which is going to sum to something finite, and finally, perhaps by dividing by that finite number, you would just hope to get a probability distribution. This is impossible, but actually we can directly check for, if we write this equation for j equals 0, right? So pi 0 equals, on the right hand side you have pi I times pi 0, and you sum over all states like this. But there is no way to, I mean, you are in state 0, you cannot really come back. There are no way to come back to state 0 from any other state. So this is all equals 0, and you get 0 instantaneously. So all of them equal 0 in this example, and therefore the sum, right, equals 0. So pi cannot really be a probability distribution in this case. So in this case, none of the non-negative solutions of this system of equation can give you a probability distribution. So for this Markov chain, there is no stationary distribution. Right? And so there may be cases where you don't. There are Markov chains for which there are no stationary distributions, and in a moment we will see the physical meaning of the stationary distribution. We will see that actually pi I, right? This number gives actually the average long-run average time spent in state I. And in this particular case, once you get to state I, in the next step you leave the state and you never visit that state again in the future, right? So in the long run, the time that you spend in that state is gonna just vanish. You don't come back. You spend only a finite amount of time. If you don't visit a state infinitely often, then the long run average time you spend in a state, it is going to be zero. In the long run, you never visit that state again, so you even forget actually that you have been there. So in that sense, all these pi i's are going to be zero. So they are actually true in the sense that, yes, yeah, so you live without ever coming back to that state, right? But then these are really trivial cases. You don't really need to specify or study the limiting behavior of these changes. That it just simply says that none of these states are important in the sense that you never visit them more than a finite number of times. So we can avoid this triviality by simply avoiding the example itself, right? So the probability in this case, stationary distribution doesn't really exist. And there are also cases where you may have more than one stationary distributions. You may have a stationary distribution, but there may be actually more than one. Example, right? So this was the first comment, and the second one is there may be more than one stationary distribution. An example again, just a two-state Markov chain with, let's say, X is a Markov chain on this state space with two elements in it, and one-step probability matrix, which is just an identity matrix, like this. Namely, both states 0 and 1 are absorbing. Right? If you start in state 0, with probability 1, you come back to state 0. And if you start in state 1, you stay there as well. Again, not an interesting Markov chain, but for this one, you can talk about stationary distribution, which also is going to give you actually, well, not exactly what I meant before, but you can actually just write down the equations for this chain as well. Okay. For example, the first one, if you write that equation for j equals 0, pi 0 equals to 1. So pi, in this case, maybe it is easier to look at the graph and you can see that, right? So on the right hand side, you will have what? For every other state I from which you can enter the state 0, right? In one step, and that's actually only state 0 itself, right? So you cannot reach 0 from 1. So this is actually, the right hand side will be like pi 0 times p0, 0. Now this is 1. Of course, pi 0 equals pi 0 will always be satisfied, right? For pi 1, you can also have pi 1 equals to state 1. You can enter in one step only from state 1 itself, So it is pi 1 times p11, which is 1, therefore you have pi 1. So you have two unknowns, two equations, and they are independent of each other. So this system of equation, together with the other one, the last one over there, right, the sum has to be 1, and we also want only non-negative solutions of the system of equations. Now this system of equations, you can put any number alpha for, let's say, pi 0, then from this equation you can just get 1 minus alpha for pi 1, and both of these equations will of course be satisfied, because these are just identities. They don't really give any information. They don't really provide further constraints. And so in this particular case, for every alpha positive or non-negative, okay, alpha and 1 minus alpha, right? This pair is a stationary distribution, and therefore stationary distributions, the stationary distribution in this case is not unique, as long as alpha is between 0 and 1. Okay, and the other case that you may come across in general, right, in an example, is stationary distribution may exist but a limiting distribution, probability distribution, a limiting probability distribution may not. Again, you can consider an example very similar to this one, but just one where you actually go back and forth between these two states rather than getting absorbed in each one of these. So in this case, we know that both states are absorbing, but in this example, so you consider a Markov chain X on, again, states, space consisting of state 0 and 1, and with one step probability, transition probability matrix like this, right? So these are of course 0. So let me just skip them, right? In this case, the state transition diagram looks like this. If you are in state 0 with probability 1, you move to state 1. If you are in state 1, then with probability 1, you move to state 0. You go back and forth. In this case, you can again look at whether you have a solution for the system of equations, whether you have a stationary distribution in this case, right? So you would just equate pi 0 to what? You can get state 0 only from state 1 in one step. So this is going to be pi 1 times p10, and since this is 1, you get pi 1, right? You can, by symmetry actually, you have a similar equation for pi 1. Pi 1 equals, now you can get to state 1 only from state 0 with, in one step. On the right hand side here again, right? You have only one term, which is pi 0 times p01. Okay? Again, this is 1, you get pi 0. As I said, by symmetry actually we know that you should get the same equation. So they are the same, and since pi 0 and pi 1 must add up to 1, right? And from this you get pi 0 equals pi 1 equals 1/2, which is positive. Therefore, it is a legitimate stationary distribution, and it is unique in this case because you can find only one solution for the system of equation. So this simple Markov chain has unique stationary distribution, but it, so let's write it, 1/2 is unique stationary distribution for this chain X, but this chain does not have a limiting probability distribution, namely pi 0 cannot really equal to this limit in this case, because the limit on the right hand side really doesn't exist. You can just look at this probability. For example, the probability that at time n you will be in state 1, starting, let's say, in state 0. So for different values of n, what are these probabilities? 1 for some of them, and perhaps 0 for some others. Because at time 0, if you are in state 0, at time 1 you know that you are going to be in state 1, but at time 2 you are going to be back. So at time 2, this probability equals 0. So for n odd, you know that this probability equals 1, and for n even, this is 0. So this is like what? So this is a sequence of numbers consisting of ones and zeros. It goes 1, 0, 1, 0, 1, 0, 1, 0. So this sequence cannot have a limit. So the limit, right, as n goes to infinity of this an sequence does not really exist. So therefore, right, this Markov chain does not have limiting probability distribution. So apparently this matrix P is not regular. And it is not regular because it is aperiodic. You can see that there is always a path from between. You can always reach one of the states from the other, even in one step. But it is not aperiodic because you can actually come back to state 0 in exactly in the number of steps which are multiples of 2. That's actually just the definition of the periodicity as well. So you look at the probability of going or coming to state I, let's say in n steps, right? Okay. For all n's for which this probability is positive, right? So you collect them all together, and you look at the greatest common divisor of these numbers. That is defined as the periodicity of that state, and that is shared actually among all the states which communicate with the same state I. So this is greatest common divisor. So this is by definition the period of state I, and this is going to be the same for all states communicating with state I. Communicating basically means, well, for all states, let's give for example J, you can reach J from I and you can reach I from J. So you can go back and that's just communication, two-way channel. There is a way to go back and forth. Right? That's also an important theorem. These are, well, the ideas are more important for us. There are too many things that I would like to discuss in the class. Perhaps I should just push this behind. All you have to know that there are such cases where, for example, if the chain is not aperiodic, then it is the corresponding chain is not going to be regular. Therefore, we are not going to be able to talk about limiting distribution. Things can fail. Right? But in many examples, we will come across regular Markov chains, and in that case, we know that now this theorem is correct. Namely, there is unique limiting distribution, probability distribution, and therefore this limit makes sense. And in the meantime, the values can be, the corresponding limiting values can be found by just solving these equations. And the solution of these equations are generally known as a stationary or equilibrium or steady state distribution. Now we are going to discuss more in detail why one would call them actually stationary distribution, right? And then we'll pick up from there and learn actually what else we can calculate about this Markov chain by using these distributions. I made all these three remarks just to warn you that things may actually go wrong in general. So we have to actually be careful in checking whether, before you start talking about limiting probability distributions, we have to just one way or another make sure that they really exist. Right? And we also had just one criterion here, right? So you check these two conditions, for example, to see whether something is regular. If they are satisfied, then the chain is going to be regular. Right? For finite state Markov chains, actually, that's even the definition. So it's, as we just wrote somewhere, right? Irreducible, positive, recurrent, and aperiodic chains. So they are the regular ones. For the discrete case, those two conditions, for finite state space, those two conditions are defining conditions for a regular chain. Okay, now, what else do I have? Let me see. Okay, why do we call, okay, we said that in general, non-negative solutions of this system of equations, right, are called the limiting stationary distribution of the corresponding Markov chain. Why is that? Why is that? Let me just keep that board over there. Right? One reason is the following. Let us say that pi, okay, so we have a Markov chain X, again on this finite state space, okay, finite state space with some regular one-step transition matrix P, right? And let us, okay, then actually, do I need to do that? Okay, we can do that. It's still okay, I guess. Pi, right, solves equations in star, and suppose that x0, right? Or maybe I should just release it. Sorry, let me just take this back. So that I don't want to confuse you with any one of these. So let's say you have just a Markov chain with one-step transition probability matrix P, and you are given, right, coming just from the sky. Somebody just gives you and tells you that. A probability distribution pi, which is the solution, right? So this is pi 0 through pi n, and this is the solution of the equations there, the system of equations, right? Now, if x0 happens to have the distribution pi, okay, namely probability that x0 equals I, right? So initial at time 0, the chain starts in the state I. If this is given by pi I, right, for every state I in this state space, right, then what can you say about the probability distribution of the state of the chain at time 1? Let's say, what is the probability that the state at time 1 is going to be J? Right? So we can just calculate this by first conditioning on the state, right, at time 0. But you remember the basic principle, so we know that this event is the same as the union of these disjoint events, where x0 equals I for all possible i's and still x1 equals j. Since the events are disjoint, probability of this event is the sum of these, the probability of these joint events, right, for all possible i's. Right? But then we can use conditional probability that x1 equals j given x0 equals I to further simplify. We can condition on this event so that we can use Markov property. Right, I can do that. Right? And in this case, what do I know? So this is nothing but the probability of going from state I to j in one step. So it is Pij, right? And how about this? So we assume that x0, right, the initial state of Markov chain, is distributed according to this pi distribution. Right? So this is then pi I. And therefore the right hand side can be written as what? Huh? It is pi j because, let's just write it one more time, as pi I times Pij, and you sum over all possible states in your state space. And since we said pi satisfies those equations, this is nothing but the right hand side of the first equation in star. And therefore it equals the left hand side, which is pi j. Right? So we conclude what? So if x0 has distribution pi, then x1 also has distribution pi. Right? And you can in fact check that this is true at any time n. Right? If, for example, xn, right, the state of the chain at time n is distributed according to pi, namely probability that xn equals j equals pi j for every j in the state space. If this is true for some n, 0 or bigger, right, then we can just check what happens to the distribution of the chain at time n plus 1. Okay? Let me also use I again here. So I or j doesn't really make any difference, right? Because these are all dummy variables anyway. So we know that this is true for at least n equals 0, and we just show that since this is true for n equals 0, it must also be true for n equals 1, namely at time 1, right here, the probability distribution of the state is again pi, right? Now I am just trying to generalize that result. So what happens if, let's say, this is true for any n? Can I say the same thing for the distribution of chain at time n plus 1? We will just argue along the same lines. So we know that this is the same as the sum of joint probabilities of that at time n, the chain is in state I for some I, and at time n plus 1, of course, it is in j. Okay? And then we can condition again on this event. Then I have this product here. And what is this? Again, in one step, this is the probability of going from state I to j. And this is because we assume that we are always dealing with time homogeneous Markov chains. So that was the standing assumption from the beginning of our discussion of Markov chains, right? And this is, if this is true, of course, pi I. So you again have what? You have sum over all i's of pi I times pij, and this is, since again pi solves those equations, right, equals pi j. Right. So what do we conclude from this exercise then? All states x1, x2, and so on and so forth are distributed with respect to pi. So irrespective of what the time is, their probability distribution doesn't really change. It stays, it is stationary across the time, and it is given by this pi. We call pi stationary because it is actually, if the initial state of the chain follows that the same distribution, then at the future times, actually, it is the new states are also going to be distributed according to the same state, no matter how far you are into the future. Okay? That's why we call pi stationary, and then we will also see actually why we call it an equilibrium distribution. There is another characterization of this distribution. Well, it's nothing but just actually rewriting all these equations, but you can give another meaning to them. Now, we will see now the next lecture that we can actually characterize or calculate long-run average cost per time unit, for example, in Markov chains, where you model the chain to grasp some operational costs. And we will see how we can use these probabilities in those cases. So let us give a 10-minute break. Okay.